So today I would like to kind of explain about some of my the set of the work for tackling multilingual speech processing, especially for speech recognition. And this workshop is actually about multilingual conversation for spoken language model. So this multilingual part, hope this kind of the talk may cover and may kind of attract the interest of this exciting research topic. Okay, so before moving to the technical content, I just want to mention. I think there are some people might be the target for this part. I quite often have a question from the junior researchers. So in this our area nowadays, it's very kind of changing, right? And many people are thinking about what kind of research we should target, especially when they decided to go to the PhD or they decided to go to the academia in the assistant professor, or they decided to go to the industry as a research scientist, and then they have to make some kind of a long-term research goal. And then my answer is usually multi something. Okay? Multilingual, multimodal, multitask, multi-speaker. Actually, we have a very good survey talk from Mark there yesterday about multi-speaker, and which is actually another very important research topic, which probably you guys can actually work on at least 5 years with these of the project. And today I will discuss about one of them, multilingual. Okay, so this is a table of contents, which little bit look weird, but do you imagine what this kind of number means? Yes, number of languages. So I just kind of following my kind of experience and introducing the scaling of the language from 1 to 4,000. Okay, first part, only one language. So for this, I just want to kind of explain about the before we move to end-to-end speech recognition, what kind of technology we are working on it to realize the speech recognition. I think that half of them here may know, but the rest of the especially junior people may not know so much about this kind of the modular-based approaches. So I also want to explain about it. We usually have a feature extraction, acoustic modeling, lexicon, language modeling, to kind of realize speech recognition. This was actually original, our kind of invention. This is nowadays people may think that no, it can be just done by the single neural network, but it's a very good division of the kind of representation, modeling from the web form to the form to the lexicon. We have a lot of resources, and then just using a language model. So by doing so, we can actually efficiently realize speech recognition. This is actually our first trial of the realizing speech recognition. And then that was actually quite a big success. But at the same time, this is actually requiring a lot of kind of effort, including the development of each of the components, which is based on different machine learning or statistical models. And also this part, lexicon, we require the linguistic resources, which I will also explain that later, so please remember this part. And then in general, with this kind of a lot of kind of knowledge, it is very difficult to build this kind of system that used to be. But nowadays, everyone is now enjoying a single neural network to solve this problem, right? Especially, there are a lot of actually the benefits, like single objective to optimize full kind of systems, or we can also removing the lexical component and so on. But the biggest benefit I would say will be that the people can actually making this kind of procedure greatly simplify speech recognition. So nowadays, actually, any people, even the student taking my course, they actually can build speech recognition by doing this single neural network. It sounds like very good, but always technology has a pros and cons. So I just want to kind of remark that I will explain about the end-to-end neural network, but I also revisit this the architecture by pointing at the pros and cons again. Okay, so let's talk about the end-to-end ASR. Once end-to-end ASR was kind of established in 2016, I personally decided to work on the speech recognition for Japanese, which is kind of, some of you might know that one of the kind of a tricky language to realize speech recognition. And this is actually one of the sentences in Japanese, so people may not understand where we kind of find that kind of word. And we actually have to providing the space chunking to kind of making the word. But I say we don't have so much explicit word concept. And then we also have a mix of four scripts. So the hiragana, katakana, kanji, the Roman alphabet. This is quite kind of usually happens. And then another kind of so this is a kind of example. So red part is actually the kanji originally from China. And you know that our ancestor made a lot of mistakes. Oh, this is not recorded, right? So I'm trying to make it a little bit casual. So our ancestor made a mistake. Instead of using one script, we try to kind of create multiple scripts and making our language very complicated. So keeping the hiragana, keeping the katakana, and we also still using the Roman one. So that we have actually four scripts. And then another kind of a difficult issue is many-to-many pronunciation. The lot of kind of homonyms and a lot of synonyms, and which actually are making the kind of mapping from the font to the text very difficult. And then another interesting part is that, well, it's partly due to that we still keeping the four kind of scripts. One of them, for example, character is only one phoneme. One of the character is actually having a 10 phoneme. And these are kind of mixed. So each character may have actually very different duration. This can be, of course, like, the 100 milliseconds or something. But this can be actually 1 second. So it's very different. So duration is also different, depending on the character and so on. So we used to require a lot of the techniques to actually handle it, especially very sophisticated tokenizer to jointly kind of chunking and providing the pronunciation, which is we really needed when we building the speech recognition system and so on. And then we always actually working with the NLP researcher and then developing a tokenizer, and then we actually handle speech recognition and so on. However, there are a lot of issues. For example, this means that, depending on the tokenizer's tools, tokenizer's result is actually different. This is actually the different tokenizer I used, and then which result in a different kind of output. This means that, if the Japanese researcher A is using the different tokenizer than mine, we actually cannot compare word error rate, which is also very kind of crazy situations. So I thought that it was kind of a most kind of difficult part of the languages, and especially in the Japanese. And then my actually the early research goal is to remove the tokenizer and then try to kind of realize speech recognition more simple form. And then the end-to-end speech recognition was actually invented. So when the end-to-end speech recognition was invented, we are very excited about it, and then we actually one of the first group to apply the end-to-end speech recognition to the Japanese language, and we got actually very exciting result, which is almost same as the classical method by using such kind of a lot of knowledge to actually chunking the text and providing the pronunciation and so on. So this is actually the great experience for me in terms of kind of removing the lexical information and simplifying the entire kind of the pipeline of the speech recognition system. Given these experiments, I saw that this methodology can be simply applied to the multilingual end-to-end ASR. Because as I mentioned, we have a postscript. We also have a complicated pronunciation. But we just using a single neural network to realize the multilingual end-to-end ASR. So that's why I kind of decided to kind of move on to the multilingual end-to-end ASR in around 2017. Okay, so now move to the first kind of multilingual speech recognition that I have been working with. And interestingly, coincidentally, many people also started to work on this multilingual end-to-end ASL, including Google and so on. So we actually are working quite kind of in the same period, and they're making this kind of exciting the jump of the speech recognition technology. So first, as I mentioned, speech recognition is classically complicated and a lot of pipeline. And if we kind of doing some kind of multilingual business and then try to create a speech recognition system, used to be very complicated. We need to actually create a lot of kind of a component. The pitch is kind of some of the parts can be merged, but some of the part like the lexicon language model, fully independent of the language and so on. So many people actually have to work on each language and then making a kind of multilingual speech system realized and so on. It's quite actually they requires a lot of resources to do the kind of multilingual speech recognition. So this is a reason that the beginning of the speech recognition is kind of done by only a few companies. When they actually often they making a market in Europe where the multilinguality is very kind of common. This is actually the reason. We need a lot of resources to create such kind of system and so on. Okay, so however, this kind of the situation is really changing by using the end-to-end the speech recognition. So before the kind of end-to-end speech recognition, as I mentioned, it is very difficult. And let's say, for example, one researcher spent half a year to make one language system, which is kind of a general our estimate about it. But by using this kind of end-to-end technologies, we can actually entirely simplify the model with a single neural network, and then we can actually solve the problem and so on. And further, how we do it, and I'm sure people here are working on the multilingual end-to-end ASR, so maybe you guys of course know, which is just kind of a combine the data, just the augmenting the vocabulary to kind of cover entire languages, including Latin or Japanese or Cyrillic or whatever. And then we also including the language ID, English or Japanese or the Mandarin or whatever, and then making a kind of a transcription and train one single neural network. That's it. So this kind of simple methodology is very powerful when we apply to the multilingual speech recognition, especially for this kind of approaches. We don't need to prepare the lexicon anymore. So this is actually one of the first end-to-end multilingual speech recognition that proposed to realize it in the kind of multiple languages. It is again our group that proposed it around 2017, and later Google is also proposed this similar approach in 2018 and so on. Okay, so it's a kind of first one of the results we obtained. So the blue one is language-dependent system. We train the model by using each of the kind of the speech recognition corpus, and the red one is just combining everything. Okay, and then actually some of the languages, especially the performance is very bad. The improvement is very large. The reason is because these languages very bad performance because they don't have enough training data. But by kind of combining all the data, this kind of other language data becomes a very good regularization, and then training is working well. And there is some degradation for the kind of very high resource language, but generally this kind of approach is working to realize speech recognition. And later we also found that after this kind of approaches, we have more data, so we can also scale the kind of a model and so on. And at that time, it is a BLSTM, but by kind of scaling the model parameter to twice, and we have a significant improvement, which is similar to nowadays we observe in the scaling. If we have more data, and if we tackle the multilingual data, And then one way is doing adaptation, a lot of kind of other techniques, but the other way is just to increase the model size, and then we can somehow mitigate the other language issues and so on. So this is our past approaches and so on. And here I actually also want to emphasize one of the technology we kind of first introduced, which is the special token. So maybe there are several other people also that they applied, but this is probably one of the first work that applied the special token to speech recognition. So this is actually quite kind of inspired by machine learning, neural machine translation techniques, but we actually including the special token, English and Japanese in the kind of a beginning of the sentence. And which means that first kind of token is becomes language identification, and then the speech recognition of this kind of language is following. And nowadays everyone is kind of familiar with kind of techniques based on whisper, but this is actually developed around 2017 to 2018. And how is that the performance of this language identification? At the time it is already very perfect, almost kind of all the cases, except for many some kind of the exception in the Dutch and the Italian. We almost having a kind of a perfect language identification based on this system and so on. So language identification and speech recognition is actually combined in this multilingual speech recognition system as well. And then I actually want to ask you the question. So actually, it was one of the easiest study in my work, and I want to ask the question. So given we have an end-to-end ASR system, okay, given we have an end-to-end ASR system, and I started this kind of work 2017. First question, how many people are involved in the core development? As I mentioned, this is a 10 language, and it used to be one researcher take the half year to build one speech recognition system for specific language. Do you have some? Can someone answer it? Okay, good. It's actually only one, only me. And how long did it take for the implementation? Again, already we have an end-to-end ASR. And how long did it take to implement this one? So this one is actually 1 or 2 days. Just a scripting. Just we collecting the data and then kind of normalizing the text and then making it the same format. So just only we do the text data preparation, and then we actually finish this kind of the implementation and so on. And then of course the training is slow, but it takes time. But after that I got to this kind of result and so on. And then I only kind of require the Unicode knowledge. At that time, I also don't know so much of Unicode, but now I was kind of familiar with the Unicode. These are only kind of language knowledge that I know. And then actually this one, after that, I submitted a paper to ASRU, and then we got the best paper candidate. Not the best paper one, but it's a kind of a very typical low-hanging fruit work. One person, 2-day effort, writing the paper. Of course, during the writing the paper and a lot of analysis, I also ask my colleague and so on, and the total effort is of course more. But in the kind of the core research part, such kind of very small effort to write a paper. So sometimes we have such an example, and usually not. So please spend your time for the effort, but sometimes you can find such kind of good research topic. Okay, so important part is actually data set for this work. And then we actually collected the various available sources and combined to realize this kind of speech recognition system by combining the LDC data and some other kind of data from Vox Proj. I don't know how many people know Vox Proj. Maybe no, right? It's before the Common Voice still has some kind of other community-driven speech collection effort. And I use this the Vox Proj and picking up 8 languages and adding Japanese, the Mandarin, and the English, and then creating this kind of 10 corpus, 10 language corpus, and realizing it. So it is also fully dependent on the kind of the great effort to collect the data. And then later, I also applied to the IAPA Babel project, which is targeting the 20 low resource languages. And then this data is also obtained from the LDC. And I do the kind of same experiments. And then we also have a similar experimental result with low resource languages. Okay, so this is the kind of first experience I had with a multilingual end-to-end ASL, and where I learned first data set is very important, and the data preparation is the key, but all other part we can actually fix it. This is actually very important other part. And then I actually also working on the code switching later by actually changing the data preparation by using some simulation and so on. This part I just quickly go through and didn't make some kind of detail, but if you are interested, please also ask me later and so on. This is very beginning of the code switching experiment where I actually combine training data by just kind of simply concatenating sentence data. Okay. And then regarding it as a kind of a code switching data, and then train the model and so on. And it's actually working to some extent. And then we also have some of the demonstration of the code switching and so on. So this is still kind of a beginning of the stage. But this Interspeech, my student and also collaborators, which is actually the activity in the Sudaya Winter School, they also actually extend this kind of methodology and extending to the 52 language, 130 code switching pairs created by using simulation data. This is actually we also presented in this Interspeech. Okay, move to 10 to 100. So again, lesson we learned around 2018. Important part is the data set. And then coincidentally, we have a lot of exciting multilingual data set collection activities, including the common voice travels and the CMU wildness data. So I can quickly kind of explain about each of the activities. So first one, CMU wildness multilingual speech data set, which is probably the first attempt of collecting over 1,000 of the languages by using the Bible sources. And this was actually led by my former colleague, Professor Alan Black. And he actually collected many of the language based on this source, and also providing some kind of alignment score of the speech data and the corresponding language. And then he also provided this kind of information. So especially if the alignment score is very high, we can safely use this language and so on. However, this has a bit access issue, and then people actually cannot get this data anymore. Next one, I'm sure many people know it, which is Common Voice, crowdsource-based approaches supporting around 100 languages, and then it's also totally over 13,000 hours now. And this one is basically dead speaking to kind of providing the speech corresponding to text in the prompt, and the people also listen to confirm it. They also recently they have a function of they transcribe them, but basically the speaking and listening is a kind of the majority of the kind of usage. And this one has a very good access and also CC0 license. And another kind of effort is by the collaboration with the researchers in Google and Meta and so on. They actually creating the low resource, the universal the speech, the recognition benchmark by kind of the following work of their kind of machine translation low resource the benchmark effort. And they created the 102 language and the corresponding speech data, and also it's a good kind of permissive license and so on. So these kind of efforts are actually directly reflected to the progress of the multilingual speech recognition. As I mentioned, the multilingual end-to-end speech recognition architecture training part, we don't have to change so much. If we have a data and we kind of providing the correct format, we can actually realize the language and so on. So after these activities, from the 10 languages, many people started to actually building many the lingual the speech recognition, like 90 languages from my colleague, 42 languages from Tokyo Institute of Technology, 100 language from Meta, and then 99 language by OpenAI Whisper. And then nowadays, many people actually think that this range of the languages, we could somehow enjoy the multilingual base. Okay, so let's move to the other 150. So this one is actually taking over the great success of the OpenAI Whisper. However, we are actually also thinking about the OpenAI Whisper has some kind of limitations, and we want to actually do some kind of a complement work with them to also contribute to the multilingual processing committee in pre-training. So for our project, which is started in 2023, is to actually the making a kind of the reproducing the whisper to kind of the mitigate the concern about open science perspective of whisper. Whisper don't have they don't kind of disclose the information about training data, or even they don't disclose how to train the model and so on, which actually, but still very great. First kind of large scale foundation model, the 680,000 hours super huge training data, and everyone was actually enjoying this kind of great progress and so on. But due to this kind of issues, we actually have a lot of potential risk of abuse, fairness, biases, and so on. So to make that kind of community better, we also try to kind of work on reproducing whisper, and that is another kind of project we are now working, and I will explain about it. But I just want to mention one thing. I don't want to blame I don't want to criticize such kind of activities. I fully understand the company's activity of making a priority for based on the kind of their competition, and then making the kind of open source reproduction as a lower priority. So my position is the understanding their kind of position. For academia, what we can do is to kind of creating the reproduction of these kind of models with transparent models, and then try to kind of complement their studies. This is actually my style. Okay, so let's discuss about OpenAI's the Whisper reproduction project, which is actually quite the big project for us, because the Whisper is the train is very large data, 680,000, and later they extend to the 5 million of the multilingual multitask data and so on. And I think people here mostly understand this scale, but anyway, usually 1,000 is large scale in the research community. 10,000 we can make a product. 100,000, 1 million is the order of the magnitude the larger than such kind of system in this kind of 2022 era. In addition, OpenAI Whisper, as you may know, have a language identification, which is the same technique as we developed before, and the speech translation, timestamp, and so on. And our goal is again to reproduce this kind of whisper style training fully based on the open source toolkit. We use ESPNet, we use all public data, which we also disclose every kind of information, including the data preparation, know-how, model check, point log, the source code, and so on. So we call our model Open Whisper Style Speech Model, OWSM, awesome. So please remember this one with pronunciation. Okay, so this other one, it's actually LGC data and open data is not good enough to cover 680,000 hours of training data. And what we have done, we also started to collect the data. We started another project called the YODAS, YouTube-oriented dataset for audio and speech, which is a collaboration with the University of Tokyo, Tokyo Metropolitan University, and CMU. And we kind of had a kind of various kind of a careful treatment and release the YouTube data. This is actually Creative Commons portion, other original Creative Commons portion data. And please note that this is not a download link. You can actually access to the audio data. So this is actually different from the other kind of other YouTube-oriented data. So, and then, so we just try to use this one, but which has a lot of issues. For example, this kind of the data has a lot of noise. Language in the kind of the speech, language in the IDE, and the language in the text, and the language speech actually very different in many data. So we actually have to process the language, the identification in the text and the speech, both sides, and then making them to be the kind of the matched language condition. And we also have a lot of speech and transcription mismatch where we have to use a kind of the false alignment and the scoring to kind of cleaning up the data and so on. So these are kind of very the classical the techniques like using CTC square and so on. But if we kind of working on the wild multilingual data, we also need a lot of kind of language identification based approaches and so on. And then by doing this kind of data, we actually increase our data finally to the 320,000 hours, 151 languages. And these all are again public data. You guys can actually fully access to this data and do the same experiment with us. By the way, this is also the similar studies are done by NVIDIA and so on. They're also using YODAS and then cleaning the data and so on. So I'm very kind of happy that this kind of data, we just released a very large amount of data with a very noisy format, and I really feel sorry about the community, but people kind of try to clean it by themselves and then try to make use of them. Okay, so by doing this kind of effort, our actually the speech recognition system is very kind of transparent and very kind of reproducible. And this is a kind of a comparison with kind of OpenAI Whisper, NVIDIA Canary, and the CMU Awesome and so on. So as I mentioned, the Whisper has some kind of issues in the reproduction. And the NVIDIA is actually great. They actually try to release kind of other information as much as possible. And the CMU Awesome is, especially for the data part, are more transparent. And this is actually a result of the English speech recognition performance. And then this is actually Whisper result, base, small, medium, large V1, large V3. And then this kind of the purple one is after we kind of include all kind of YODAS data, and then we get this kind of performance. Okay, it's slightly better than the Whisper in some specific English test set. But the more important part is that we also prepared a non-autoregressive the CTC version, which is actually way faster, and then we can actually having a similar performance, but very kind of fast inference based on our kind of the technology and so on. But this is for English, and how about other kind of languages and so on? Of course, we have some experiments. So first, by using the YODAS data, from V3.1 is without the YODAS, and V4 is YODAS. We actually got a kind of significant, please check the kind of average. We got a kind of significant improvement by using such kind of large data and so on. And then our the ASR system is at least better than Meta's MMS models. And then our performance is still kind of Whisper is very good, but comparable to the kind of Whisper medium the size and so on. But the still Whisper large V3 is kind of very good for the multilingual processing. And then as I mentioned, our kind of decoding is much faster. And this one is actually our recent effort of the awesome latest project, and we submitted this one to the Interspeech. And yesterday, we got the best student paper one. I'm very happy about it. Okay, and then I also, through this kind of process, I kind of accumulate a lot of know-how of how to deal with the multilingual processing and so on. So if I have time, I can kind of also explain each of the time, but for now, I kind of skip this one. I also released this kind of slide later to you guys, so please also check it. But there are a lot of know-how we actually have to deal with. And given this experience, my impression of the multilingual speech recognition, 150 or probably up to 200, I think we can scale it. So I say our kind of technology, even some of people mention, some of the languages in Whisper we are, same for author, it's not great. But based on this experiment, it is probably possible by just continue this kind of methodology, because we can still find a native speaker for this kind of 150 to around 200 languages and so on. If we have a native speaker, we can of course collect the data, but more important part is whether we can verify the data, it is correct or not. Again, our kind of project is that also working toward the thousands of the languages, where I actually cannot find the people that can speak this language. And so some of the language we really don't know it is really kind of correct or not. So this is probably I think it's a kind of one of the kind of critical threshold. Around the 100 or 200 would be the kind of method that we can actually making this kind of work as a kind of end-to-end current methodology based on current methodology. So based on this kind of setup, we also creating a new benchmark called multilingual SPARK, which is a kind of next part. And then this multilingual SPARK project is, again, as I mentioned, we targeted this kind of 150 language which we can somehow handle. And then, of course, as I also mentioned, and the people already know, some of the low resource languages, even this 150, it's actually some of the language has a very kind of bad performance and so on. So this multilingual SPARK benchmark is not only focusing on the performance of the average across the languages. For example, our original design was kind of a character error rate for all language by taking the average and the language identification. Okay, but we don't know. Maybe some of the low resource language performance is very bad. This kind of our system might actually include some kind of biasing issues based on our kind of distribution of the data and so on. And unfortunately, this number cannot be fully kind of interpret what's happening in the kind of the inside. And of course, one side of the approach is to checking the entire kind of 150 performance, but which is actually too much to actually check the kind of performance and so on. So multilingual SPARK 2.0, which is also, again, we actually presented this Interspeech, we actually having additional metric to consider the fairness, bias, and so on. First one is we check the worst 15 language, and then taking the character error rate. This is a kind of another metric. And the second additional fairness metric is to check the standard deviation across the language. And we also adding the dialect, accent speech recognition. That's why I mentioned 150 plus 50. Actually, we include the additional 50 accent, the dialect, the speech recognition, and so on. So by doing this kind of a measure, we can actually also consider the fairness, accessibility, and the inclusion based on the accent, based on this benchmark and so on. And as you can see, one of the models, Zeus, is actually very good performance in the overall character error rate, but turns out that the MMS is actually better for the fairness, inclusion perspectives and so on. So this is a challenge we designed and so on. Okay, so this is up to the 150 languages, and now I move to the order of 1000. However, as I mentioned, now we cannot use the current protocol. We actually have a difficulty of finding speakers. So we actually definitely need to change the methodology and so on. And then I will explain about the two of our the group research activity to handle this kind of 1000 language and so on. First is semi-supervised approach. So this setup, again, in the order of the 1000 languages, even we cannot get the speech data. We don't have a speech data. However, interestingly, we can get a lot of linguistic resource. Many computational linguists, field linguists, they actually collect a lot of kind of linguistic resources and then summarizing this to the kind of the unified form. So this is a very interesting setup. No speech data, but we have a linguistic resource. How to then create a speech recognition and so on. And unfortunately, end-to-end ASR cannot be used for these approaches because they don't have a layer of the lexicon resource and so on. Instead, we use the classical pipeline. And remember that the classical pipeline of the speech recognition, we actually have some kind of the form representation, which is designed to be, actually not so much, but it's designed to be language independent. Okay, so from here to here, we actually making something language independent. We can use the other languages. After that, from lexicon to language model, we just using the resource from the such kind of the linguistic information, and then we can get a phonetic dictionary. And we can also, they also collecting several kind of word usage and so on. So we can also get some n-gram statistics, and then we can actually build the speech recognition and so on. By doing this kind of approaches, we don't need the parallel data. We even don't need a specific target of the speech data to create a speech recognition and so on. And for the linguistic resources, we collect the various people's great effort, like Arovera and Hobio. Some of them are actually done by my colleagues in CMU. And lexicon, we use the Grotlog, and the n-gram language model, we use the Kurubatan database and so on. And then, but these are kind of great resources. They actually cover totally around 1,000 languages. So we can actually possibly build in 2,000 language. And this is our work 3 years ago. We actually used combining this kind of resource and so on, and then showing the proof of concept that by using this methodology, we kind of creating the IPA form-based acoustic model, combining these resources, and we can showing that possibly we can build 2,000 language ASR system. We call this project ASR2K. So if you're interested in that, please ask me later or check this paper and so on. And through this process, we also learned a lot of things. And I think that one of the important research topics may be revisiting form information. So first, many of the low resource language is actually they don't have their own script. So they use a Roman alphabet or they use an IPA. They don't use actually IPA. The linguists actually use IPA to transcribe their the speech and so on. So the IPA form is very important for this research direction and so on. This IPA approach is also very important for the other kind of project like language learning or the speech therapy or disordered speech and so on. So I think we should, our community should also revisit this kind of IPA form based approaches and also try to build a kind of IPA form based very high accurate the speech recognition system. However, my experience, IPA phone is very difficult to do it. I even don't know half of the symbols, and the linguists also they cannot really use them. And they also have a slight dialect, and then it is not. This theoretically is very universal, but actually it is not very universal. So IPA phone has a lot of also issues and so on. So I also hope we can also consider to revisit the phone unit and so on. And again, this kind of motivation, we are now revisiting the phone the model and try to build a phonetic foundation model. So if you are also interested in this kind of project, please also reach out to me. Okay, so another kind of project now move to 4000. This is self-supervised. But note that this is not speech recognition. We just kind of train self-supervised trained model, and if we have some target language, we can just adapt it. Okay. In this kind of particular setup, we can only have a speech only data. There's no the corresponding text data, and how to utilize this kind of models and so on. And of course, everyone knows self-supervised learning is kind of good the solution to provide a pre-trained model. At least in the model knows this kind of languages in the kind of pre-trained stage. But again, how to use it is because very difficult because we don't have a parallel data. And similar to the awesome project, we also try to kind of build speech foundation model from scratch, based on our kind of public data and the open source toolkit and so on. And this one is corresponding to my presentation of this part, GEUS, which is a cross-lingual encoder for universal speech. This is basically crawling the large-scale data from the web, but of course we kind of care about the license and training the models by using the WebLM style, but we also adding the evaluation to make it further kind of robust against such kind of acoustic variation, and then we actually train it based on the ESPNet. And similar to the awesome project, we actually release everything. And of course, this is not just a single project. There are a lot of great initiatives. Again, I really kind of acknowledge my former colleague, Professor Alan Black. He is the kind of first person to kind of initiate and discover the access to the thousands of the spoken languages. And then later, Meta, MMS project is partly using his kind of a methodology, and then extend their data to the thousands of the languages. And then we follow this methodology and further extend their language to the 4,000. And this is the kind of the database we use, and totally $1 million. It's actually larger than the awesome project because we don't need to actually prepare the transcription. So it is actually relatively easier to collect the data and so on. And we also use the YODAS data to also creating this data and so on. And we also showing the totally 4,000 languages. We collected totally 4,000 languages. By the way, the most of the languages comes from the religious region of the languages. Okay, and then we actually have a kind of creating the new self-supervised learning model trained from scratch, called again GEUS, and apply to the first version of the multilingual SPAD, the benchmark and so on. And these are more like the other methods like WebLM, Excel, STRAL, MMS, the Web2Vec, BART, and so on. So all of these kind of a method is trained with the big companies. But this one is from kind of the academic institution to create this kind of self-supervised learning models from scratch. And then we can also get a kind of a reasonable performance compared with them. This one also having the perfect transparency and also having a good kind of a performance across the task and so on. And again, this kind of a work got the best paper award in EMLP. So one of the messages is if you want to get the best paper, you guys can work on multilingual, and then you can get the best paper. But this is actually very kind of the interesting achievement. Usually, of course, as you may know, EMNLP, the NLP conference, right? Speech people are not so kind of the dominant. And some of them are working on speech, but not from, you know, our speech laboratory. It's more like an NLP laboratory, they work on speech and so on. And this one is a kind of a core speech topic, core speech laboratory, submit a paper to NLP and getting the best paper out. So this means that, you know, our technology, our kind of a problem is very kind of universal, and the NLP people can also recognize our kind of such kind of other programs and so on. Okay, so by the way, how many minutes that? Okay, so I actually have a couple of other slides after the summary, so I just want to do it. Yeah, apologize for that. Summary, as I mentioned, the scalable neural network based on end-to-end approaches at least can work until 100 or 200. So this is the one of the efforts we should definitely do it, and we can work on it. However, if we go beyond that scale, goes to the 1,000, probably we need to change the methodology. And then the one approach is the universal form-based approaches. And the other is not the solution, but just kind of, you know, the one way to use this data, which is using self-supervised approach and so on. And as I mentioned, the whole unit is very important to revisit. However, this is again just a proof of concept work. And honestly, I am not very sure that this kind of 1,000 language effort is actually valid technique. Why? This is again because we actually cannot find a speaker for this, the language and so on. So this is actually a very difficult problem, but I just also introduced one kind of activity I had with my kind of other colleagues for this kind of problem and so on, which is endangered language documentation. I have a kind of close collaboration with the anthropologist, and then they actually visited the village in Mexico and collecting one of the other endangered language and so on. And they actually also had a lot of effort to create 100 hours of training data with corresponding kind of transcription and so on. I helped with their project and built end-to-end ASR. And it turns out that this kind of end-to-end ASR system, its performance is actually okay. It's not an expert transcriber, but similar to the performance of novice transcriber. So they are very happy that this kind of technology can actually accelerate their transcription, the effort and so on. And but this is a very, very rare case. We don't have so much kind of the large data and so on, and it is also not easy to kind of work with such people and so on. So my the last message is that toward the 1,000 of the languages, probably we should work on each language one by one. We have tons of issues for such kind of language and so on. Few speakers, limited infrastructure. Since it's a village, even we cannot use Wi-Fi. Also community trust. Such people don't understand the technology. They don't want to donate their voice and so on. We have a lot of kind of careful discussion with them. It takes very long time to collect such kind of data and so on. But these kind of efforts are done by many field linguists, anthropologists, and so on. So probably the possible way is for us to work with them and try to kind of establish such kind of technology one by one and accumulating it toward 1,000 languages and so on. So this is actually, again, cannot done with a single researcher or a single group. So I would like to really kind of ask you to work together for such kind of goal of ultimate the accessibility, and also try to kind of preserve our culture. Thank you so much.